Can you hear me?
Yes,
Yes,
sir.
sir.
All right, let's try that again. Okay. So if you had your readings looking like this, right? If you had the readings looking like this, when you're presenting your data, right? It should not look like these. All of these should have the same amount of significant figures, right? So when you're presenting the zeros, these zeros are called what kind of zeros?
Trailing zero.
Exactly, trailing zeros. But because of this 6.401, because of this 6.401, all of these have to also have a trailing zero, right? But if it's a case where if you didn't have this 6.401, right? If you didn't have this one right here, then you could get rid of these zeros. All right, but this is only when presenting a table. But if you're presenting an answer, right, you would get rid of those trailing zeros. So you would only have like 6.4, only have 6.4, right? But if you're presenting in a table, all right, let me not use that one. Let me use this one. Because you're presenting a table, you have 1.800. And because there's one down here, all of these need to have the same amount of significant figures. So therefore, we add trailing zeros. But because if we didn't have it in a table, right, then you could just present it as 1.8 if you were just presenting an answer, right? But because it's in a table with 6.401, you have to add these trailing zeros. So is that clear?
Yes, sir.
Yes, sir.
All right. So each of these measurements has only two significant figures, and we want to go to to standard form. We can look on that quickly. And let's go back to ensure that we're all here. Okay. Right. Oh, and we forgot these. We forgot these as well. So leading zeros. So which zeros, which zero digits are not significant figures, right? Which zero digits are not zero significant figures. So we have leading zeros before real numbers are not considered significant figures. So therefore, we will place these in standard form. We'll place these in standard form because they are not significant. And we'll go to that next, right? Trailing zeros after real numbers if there's no decimal is written. So remember, right? If there was a decimal here and we had some more zeros, we could omit those. But we have to include these zeros because it represents a part of the number. So if we remove these zeros, what would happen? This would not be 1 million again. It would just be one, right? So therefore, these are very important zeros. So we include them in our answer. But for leading zeros before real numbers, we have to use standard form. All right, so standard form is presenting our answer, right, that it looks good on the eye, right, scientifically. And I think it's called a scientific notation. Whenever we're presenting our answers, it should look something like this. So if we had 0.00000, see this here, 0.0000099, right? Which one looks much better, this one or this one?
9.9, sir.
Exactly. So the 9.9 times 10 to the negative 5 meter is it looks much better on the eye. So therefore, in order for us to get here, we put in standard form, right? And how we do that is we multiply this answer by times 10 to the negative 5. It's very easy to do, right? You just go like this: 1, 2, 3, 4, 5, and then this you would stop in the middle of the first two significant figures, right? So these answers should only have two significant figures. So let me do that again. We have 0.00009, 4 zeros. Now we multiply by times 10 to the negative 5, right? But you would do it like, if you have the number looking like this, you say 1, 2, 3, 4, 5, and you place your decimal point there. And because you're moving from left to right, right, you're causing a decimal, right? You're causing a decimal to like a whole number. It would have a negative. It would have a negative. Let's do this one as well. So let's do this one together, right? So this will be 1, right? Then 2, then 3. So you would have 7.1, net decimal point will be here. You'd have 7.1 times 10 to the negative 3 meters. All right, let's look at this one as well. We have 0.42. If you're moving this to say two significant figures, you would have just one. So therefore, you would have 0, 1. So your final answer would be 4.2 times 10 to the negative 1. Is that clear?
Yes, sir.
All right. Anybody want me to go over that again?
Yes, sir.
All right. So I'll go over the last. I'll go over the last one again. Right. So if we have 0.00099, right? In order for us to get this to two significant figures, we have to multiply, right? Or we have to change it to standard form. And the way that we do that is by timesing it by 10 to the negative 5. Now, the way how we determine how much we will times it by, we do this as an exercise of going 1, 2, 3, 4, 5, and replace the decimal point in between the first two significant figures. So because this is 1, 2, 3, 4, 5, we're moving from left to right. Therefore, we would have 9.9 times 10 to the negative 5 meters. All right, are we better now? We clear?
Yes, sir. It's always negative.
Right, that's what we're going to next, right? It's not always negative. So you had 1 million here, right? You had 1 million here, and they wanted you to change this to standard form, right? You had 1 million. That's a lot of zeros, right? So you want to change it to standard form, right? Let's do this one. How much? What would be a standard form here?
Sir, 6.
Right. So let's hear it. What would the final answer be?
1.
So I hear 1.0.
Positive 6.
Right. So 1.0 times 10 to the positive 6. Everyone gets that?
Yes, sir.
All right.
Sir, repeat, sir.
All right. So we have 1 million here. All right. So we have 1 million here. We have 1 million here. And we are required to change this to standard form. All right. We want to make the answer look professional and scientific. So we would change this to standard form. Now the way that we would do this is by 1, 2, 3, 4, 5, 6. We would place the decimal point between the first two numbers. So we end up with something like 1.0. I'm not using my stylus, right? So forgive me if it's a little choppy, right? Times 10 to the 6, right? Because it is 1, 2, 3, 4, 5, 6, and it is positive because over here we were using decimal points. It was decimal, right? So we're changing the structure of this big number, right, into a smaller number. So therefore, we're positives. We're moving from right to left. So whenever we're moving from left to right in a positive, in a decimal situation, it would be negative, but we're moving from right to left. So therefore, it would be positive. All right. So are we better now?
Yes, sir. I know.
All right. All right. So these zeros in these measurements are not significant, right? Remember we talk about trailing zeros, right? But if we were supposed to present these in an answer, we would convert them into standard form, which would give us one significant figure, right? This would also give us one significant figure, right? And this would give us four significant figures. So the question asks you, if this question asks you to convert this to two significant figures, let's just say this question asks you to convert this to two significant figures. How would you go about doing this?
Sorry, let's say two significant figures in the like 2 and 7,
Right?
and then the one beside it, you're gonna see if he higher or lower than 5, and depending upon that, you're going like what two,
Round
sir?
up
You're
or
going probably just
round down, right?
yeah, you're going probably be 27.
Exactly. So are we all seeing that?
Yes, sir.
All right. So you have done significant figures before.
Yes,
sir.
sir.
Yeah,
Yes.
in maths.
All right. So in mathematics, so let's just do this one. So we first move this to two significant figures, right? So we'd say 1, 2, 3, 4, right? And we place the decimal point in between the first two significant figures. So we end up with 2.7. And you would look at the third significant figure here to see if it is higher or lower than 5, and therefore we would
You can
round
make it
up
still.
or round down. All right.
3 point.
So it will be, we would do, let's just say a question asks for two significant. Right, just two significant figures. So there will be times 10 to the what?
Sir, 27 or
4.
2.7.
Right, 2.7. So times 10 to the 4. All right. Okay. All right. So now we move on to errors. Right. So we have less than 8 minutes. So systematic errors, we can move on to the types of errors and see how far we can go with this. Systematic errors are also called bias errors. So they are consistent, repeatable errors. For example, suppose the first 2 milliliters of a ruler are worn off. And we know these types of rulers, right? And the user is not aware of it. So everything he or she measures will be short by 2 milliliters, and that we would classify as a systematic error, right? Because it is always repeating, it is always consistent. All right. So systematic errors arise for many reasons. Here are just a few. So we have calibration, due to non-linearity of errors, right? Or errors in the calibration method, right? So we haven't calibrated our our devices before we start to use them, right? Say we're taking the mass and we didn't zero the top band balance. We didn't ensure that it's at zero with nothing placed on it. Then all our readings would be off. So in the calibration method, we would fail basically in our calibration method and we get a lot of errors. The next one is loading or intrusion errors. The sensor may actually change the very thing it is trying to measure, right? So say we're trying to measure something and we, while measuring, we alter something. Let's say for example, we had a thermometer, right? We had a thermometer in a cold environment, or we were measuring a cold glass of water and we took that glass of thermometer and we placed it in hot water, right? Would that affect the measurements of the hot water?
Yes.
Right,
Yeah.
because that would pull some of the heat. All right, so that would be loading or intrusion error. Spatial error arises when a quantity arises in space, but a measurement is only taken at one location, right? So say we want to find the temperature of the room, want to find the temperature of a room, we have an experiment where we want to determine the temperature of a room, right? But we only take the temperature at one section of the room. What about the other side? What about at the top of the room? Because usually the top of the room is warmer than the bottom. Why?
How does the heat come from first?
All right, that's one answer, but I'm looking for something else. Why is the top of the
Why there's
room?
a higher concentration at the top of the room?
Go again.
There is a higher concentration at the top of the room.
All right, that is also good. But hot air rises, right? Hot air rises, cold air falls. So the top of the room would be hotter, right? The top of the room would be hotter than the bottom of the room, right? And also, if we're using zinc and the sun is on the room, is directly on top of the roof, right? The place will get hot from the hotter sections of the roof. All right, so we have human errors arise if a person consistently reads a scale on the low side, right? So let's say this person does not know how to read a meter ruler, and they consistently read it right below. Every reading that they take is 1 centimeter below, or 1 millimeter below. As we saw before, all the readings would be off by 1 millimeter. The last one here is the defective equipment error, and this arises if the instrument consistently reads too high or too low due to some internal problem or damage. All right, so we want to ensure that our instruments are up to speed and are not damaged. So are we clear so far?
Yes, sir.
All right. So the next set of errors are random errors. These are unrepeatable, right? And they are inconsistent errors resulting in scattering the output data. So random errors of one data point is defined as the reading minus the average of readings. All right, this might seem unclear, but you just want to make note of the fact that these are unrepeatable and inconsistent, right? So
Sir,
what to define random errors? Question?
sir, mute everybody, please.
All right, so I'll try and be more alert in that regard. Sometimes I'm not able to mute. All right, so let's move on. Yeah, so you just need to know that they're unrepeatable and inconsistent. You won't need to necessarily um, define them or explain random errors. So some random errors could be parallax. So this error can occur whenever there is some distance between the measuring scale and the indicator used to obtain a measurement. So if the observer eye is not squarely aligned with the pointer and the scale, right, the reading may be too high or too low. Some analog meters have mirrors to help with this adjust alignment. All right, to help with this alignment. So therefore, um, you read at different points during the experiment, right? So at one time you read above, and one time you read below, right? Your eye level should be in line with your reading. So if you have to stoop, if you have to stand on something, a small stool to get your readings, right? You have to do that in order for your to eliminate parallax error. All right, so environmental errors. So be aware of your errors introduced by your immediate environment, right? So you may need to take account for your to protect your experiment from vibrations, right? So we're using a table, and we require the table to be stable, right? You want to, and you if it's a case where you cannot avoid the table being stable because of the type of table, right? But you want to make note of that. You want to make note of changes in temperature, electronic noise, or other effects from nearby apparatus. Let me see how much slides you have left. And then let's go through this last one for the last minute, right? So reading error described such as parallax error, as you just said, interpolation or optical resolution, right? Loading error results from the change in measurement instrument when it is being used. The effect of support, dirt, human error, reaction time in starting and stopping. There's stopwatch. This should be stopwatch. All right, so I will post these as soon as possible. It's 9:41. We are over time. All the best. Remember your test on Wednesday. All
So
right.
you're not going to do any revision? Sir?
Go again.
Are you going to do any revision?
Revision for the test.
Sir,
We won't be able to do that, right?
sir,
Yes.
about the thing that the work that you sent, sir, can you at least give us some more examples or other way it can be like worked or whatever, because feel
Sir,
like
you get
make me learning or no.
All right.
Sir, next class, we're gonna topic here, sir, cause me not fully understand it yet, you know.
All right. I won't be able to
sir,
do
you
that.
get
Sir,
more.
me too. Come
All
to
right.
understand.
I'll check if I'll check if the work was sent, and we'll revise quickly next week. All right. All the best, everyone.
All right, sir.
All right.
Bye,
Same
sir.
to you.